This was a hard talk to prepare for. I didn't realize that there actually is a course on topological data analysis given at this university, which is pretty rare. I mean, it's not done frequently. So I thought that it was going to be my job to explain what topology is, explain what data is, explain what data analysis is, and then explain what topological data analysis is, and then tell you what are the problems and the frontiers, and do all that within an hour. So it would have been a little bit easier had I known that there was some preparation. When I found out that there wasn't going to be a blackboard in the room, I realized that I have to prepare slides, which made me realize that I had to scour the internet for images that I could steal and produce my own pattern to go with. So, yes, so my goal is to explain all of this stuff and oversimplify it to the extent possible. So let me start off with topology. And it's not, so topology is usually called the rubber sheet geometry. It's supposed to be you're supposed to imagine that you look at objects, but you're willing to stretch them, you're willing to pull them, you're willing to do deformations of various sorts, but you're not allowed to tear them. Or if you do tear them, make sure you sew them back afterwards exactly the way you tore them. Okay, I mean, sometimes it's necessary to be a little bit violent. So this has a subject, it's really a 20th century subject, but people frequently attribute its creation to Euler from, I think, the 17th century, and the bridge of Königsberg problem. So this is taken from Euler's paper. It's the one bit of historical work I did because I was able to get it off the internet, without any effort. So yes, like all of Euler's other papers, it's written in Latin, but it doesn't really matter. Okay, so this is supposed to be various land masses that are connected by bridges, and the puzzle at the time was, can you go over all of the bridges without, make sure you go on all of them without going on any bridge twice. Okay, and by the way, and if you look on the internet or in Google Scholar at topology, the vast majority of the time that the word topology is used in practice, it does mean graph theory, which is the kind of math that this is embedded in, rather than what topologists call by topology. And I don't know who wins, whether it's the population at large or the specialists, but this does capture some very key ideas in topology. One idea that it captures is, Euler's great insight was to completely oversimplify the problem, right? Don't go ahead and try to do measurements of, how long the bridge is and this and that. He just said, every landmass will be represented by a blue dot. Well, or something in Latin that means blue dot. And, each bridge you encode by an edge, and this is the structure that we call a graph. And then his observation was just this, that if you have a vertex with odd valence, with an odd number of bridges going out of there. So then think, if you didn't start there, so then you have to go in, you go out, and then you go in. So you have to end there. So if you have more than two of those, you're in trouble because both of them want to be the place where you end up. Okay? So that's what makes it impossible. So it's a very, very straightforward argument put together. I don't know how many fights in bars over, over there in Königsberg over the years, but so this was sort of what people give Euler credit for. But actually, the thing that was much more important for topology was something that is called Euler's formula, which is, suppose that you take a convex polyhedron. So you know what a polygon is, because we've all read Euclid. So a polyhedron is something that's one dimension higher. Okay, so that instead of just having, vertices and edges, right? You'll also have two-dimensional faces. Okay, so you imagine that you have, say, a convex polyhedron, polytope like this. So it has lots and lots of vertices and edges and faces. Okay, so like this is the easiest one. This is the analog of the triangle. It's called the simplex. Okay, so you imagine a pyramid whose bottom is a triangle. Okay, so if you do that, you'll see that there are 4 vertices, 1, 2, 3, 4. There are 6 edges, 3 around that vertex on top. Okay, and then there are 3 on the bottom triangle. Okay, and there are also 4 faces. Okay, so you calculate V minus E plus F, and you get 2. Okay, that's a great thing. Now you can imagine what happens if instead of I made a pyramid whose bottom was a triangle, suppose you did like the ones that you study about on Pesach, where the bottom is quadrilateral, doesn't really matter which one. You would discover the same thing holds, and it's a complicated, interesting theorem that V minus E plus F equals 2. So this was a relation that Euler discovered about okay, we would nowadays phrase this as saying that the Euler characteristic of the 2-sphere is 2. That's the way this would be phrased nowadays, but that isn't what Euler said, and he didn't even say it in Latin, right? Because he was too humble to name this quantity after himself. And also he was only interested, he thought, you can't name the number 2 after anybody, and for him, it was only relevant was that this quantity was always the number 2. This became a very, very popular thing when it was shown to imply the 5-color theorem. This thing about if you have a graph in the plane that you can color it always with 4 colors. That was only proven by Haken and Appel in the 80s, in the 70s or 80s. I mean, it was done, middle of last century, a very impressive computer proof. But for a century before that, people knew that 5 colors suffice. And the key tool in that was this formula of Euler. But the topologist, firstly, doesn't really care so much about convexity. So what you should have imagined in Euler's first formula is, suppose I just took a blob of clay. Okay, so it doesn't have to look at all like a sphere. Just make it a blob and keep it blob-like, blobbish. Okay? And then I go ahead and I draw, and then I take the thing and then I imagine, putting vertices and trying to make the parts of it individually as flat as possible so that it's made up out of vertices, edges, and faces. Okay? And then I just go ahead and compute this. As long as that blob is a blob, so then its boundary will be a 2-sphere as far as a topologist is concerned. Okay? And this quantity will always be, even when it's non-convex, it will always be 2. But if you were to look at the surface of a bagel, and this is how a topologist might look at the surface of a bagel, okay, the quantity always adds up to 0. Okay? Or, for example, one way to see this is if you were to think of this thing as somehow being a product of 2 circles. So a circle I'll imagine as being a polygon. For a polygon, the number of vertices is always equal to the number of edges. Right? I remember asking my daughter, what's the definition of a pentagon? And she said, oh, it's something that has, 5 vertices. And I said, what about if it has 5 edges? She said, also. Okay, that's also the definition. Yeah, they're both right, because for polygons, vertices equals edges. And a torus is a product of 2 circles. And if you think about that, you could quickly see that vertices minus edges plus faces, all the faces are somehow associated to products of 2 edges in the polytope. So it's a little exercise in algebra that you would be getting this relation. And the amazing thing that was discovered not by Euler, but by somebody or other, I don't really know who. I'm guessing Poincaré, but it doesn't really matter. Oh, it does matter because I'm being videoed. So I should not express uncertainty. I should just say, yes, it was discovered by Poincaré, very early in the 20th century that this quantity here, even for higher dimensional objects, if you take vertices minus edges plus faces and then subtract off 3-dimensional simplices and so on, that alternating sum is a topological invariant. When you smush your object up in all sorts of different ways, you get the same answer. So that's a quite remarkable thing. Okay, but now this is stuck. I don't know. Okay. All right, so it wouldn't be a topology talk if we don't mention the Mobius strip, so I have to. So that's a Mobius strip. You see, the trouble is I don't remember what my slides look like. Anyway, so yeah, I'm mentioning it because it's a cool thing, right? I mean, it looks like a strip, but you take a piece of paper, you glue the 2 ends together differently. It has the property that if you start off on one side and you go around, it ends up on the other side. Unlike a usual strip of paper, where the boundary consists of 2 circles, Okay, in this one, the boundary consists of one circle. When you start on one edge and you actually you can get through the whole edge of this. So this usually is used to introduce the idea that's a more abstract Mobius strip. Okay, and here's another way that you might think about it, and just to get the theme of how topologists like to abstract things, is suppose that I wanted to make a space that was based on 2 points on a circle. So one point, so this is what my space consists of. So if okay, let's start off simpler. What's the space of 1 point on a circle? What are the possibilities for 1 point on a circle? Well, the answer is the circle, right? I mean, because the point could be any of the points on the circle. The aggregate of all of the possibilities of the system whose state is determined by 1 point on a circle is just by definition the circle itself. Now, I suppose I was interested in a more complicated system, right? I mean, so I'm living on the edge, right? And I'm living just on a circle, okay? And I want to now imagine a system which is secretly propelled by 2 points on the circle. And I want to know, how would I keep track of such a system? So I could think of it as being, okay, so if I think about a circle as being an interval and then I identify the points at the end, okay, then when I take a product of two of those, which would be, 2 points on a circle, right, so that would be a point, comma, another point, okay, then I would get the torus. Okay, so that one's easy. But now suppose that it doesn't matter which order I consider the 2 points. Right, there isn't a first point and a second point. The points are indistinguishable. Okay, right? I mean, right? They're electrons or something, right? So now, if you begin trying to think about what this would look like, there are a couple of ways of thinking about it. One way of thinking about it is that I have this torus, and then I identify the point here with the point there. These opposite points around the diagonal. And what I claim is that you actually get a Mobius strip. So this is where a Mobius strip would occur very naturally if all you were thinking about was a circle. Okay? To a topologist. One way to see that is, well, there's this, if you were to look at this quotient, right, this kind of identifying these different pairs of points, well, for the points that are, say, not on the diagonal, each point is made the same as one other point. Well, the points on the diagonal, they're not different than, they're not identified with any point other than themselves, right? In other words, if I have something that's x comma y, that's the same thing as y comma x. That has two representatives for what it is. If I have a point that's of the form x comma x, it's not the same as anything else, right? There's only 1 point. So that's sort of like having a piece of paper and folding it, right? If you fold it along the diagonal, right? Then you would be identifying the point above and the point below. So that makes you think that this could be the Mobius strip. After all, the Mobius strip just has one boundary piece, right? And that is, in fact, the image of that diagonal. And one way to do this would be to just try to break the symmetry. So first I'll write the first guy, and then I'll look at where the second guy is. Okay, and once I move 180 degrees, okay, in this direct, right, if I move, right, imagine my 2 points, and then I begin moving 180 degrees. Once I move to that, then it's exactly the same thing all over again, just reversed. So you would so this is a way of getting the Mobius band, the Mobius strip. Okay, this is another view of the Mobius strip, which is, again, every topologist loves a Mobius strip. I mean, so you can't see it enough times. But what's sort of cool about this one is that this looks like half of a bottle. Okay, and that bottle is called the Klein bottle. Okay, and the Klein bottle is sort of like the Mobius strip. Okay, so you imagine that you were to have a tube, and you identify the two ends of the tube with each other, right? So I have a tube, but I'm just looking at the boundary of the tube, right? So I mean, it's a tube. It's not filled with water or anything. It's filled with a vacuum. If you could be filled with a vacuum. Okay? So when I identify two of them, if I do it in the most natural way, I get a torus. But don't do it the natural way, do it with a twist, like in the Mobius game. Okay? If you try to do that, you'll discover that you can't really do this in three-dimensional space. The picture you'll get looks like this. Okay? It's a very, very beautiful natural object, but there's this place where it intersects itself. You're not, in the real live Klein bottle, those points don't intersect each other. So you can't, unfortunately, draw a Klein bottle in 3 space, and it's even worse on a projection screen. One way you could imagine this, if you wanted to, is you could create a 4th dimension by mind alone, just invent a color. When you draw things, don't just have them like this. Pick some extra color like red and decide on its intensity. Okay, and then you just have this Klein bottle blush as it goes through itself, and then you realize, oh, in that R4 direction, in that fourth dimension, this thing here goes over that and connects on the other side. So that will be the beautiful Klein bottle, which seems like a topological invention. It's sort of a strange surface. It has the Mobius band non-orientability, but without having any boundary at all. And it was, certainly when Klein invented it in the late 19th century, was just a curiosity. Okay, so I want to now end my introduction to topology and just talk about what are some topological notions. Okay, so one notion that topologists will talk about is they'll talk about the number of components that a space has. So far, all the spaces we talked about were connected. They just had one component. But I could imagine, but I could think about, I don't know, there are all sorts of other spaces, like the space of my ears, ignoring my head, right? That will be a space that has two components, okay? There's the notion of dimension, which is a very subtle notion. There are few Nobel Prize in economics that are indirectly just consequences of the way dimension was developed. So for people who've taken linear algebra, there's a notion of dimension based on how many vectors it takes to span a space. But what happens if you're allowing nonlinear transformations? Okay? So if those transformations were smooth, then the whole idea of calculus is that you approximate your functions by linear ones, and then you pretend, and you do the best you can. Okay? So that would work. But suppose that your things aren't even smooth. Is there still some notion of dimension? So you have to be careful about this, and there are fractal dimensions, and there are all sorts of different dimensions, but there is a notion that actually just depends on the topology, okay? And that's sort of an interesting, subtle thing. I don't think that I can talk about fundamental group and homology except to the people who already know what those are, and if they know what they are, then there's no point in me discussing it with them. So, okay, Euler characteristic, that's the thing that I just told you all about as being what I feel is the first real topological discovery. That's the thing that vertices minus edges plus faces is really an invariant of the object. It doesn't matter how you triangulate it and how you subdivide it. And this is really a fascinating thing because this quantity behaves a lot like volume. And it's a very strange thing, because volume is something that's really metric dependent. If you take me and then you just scale me by multiplying me by 2, my enormous weight will be multiplied by 8 and be even worse. Okay, right? I mean, volume is completely metric dependent, right? If I would be squished really small, okay, well then I'd be a black hole, and but my volume would be small. My weight might not change. Euler characteristic also has this property, right? The number of vertices when you take a union, the vertices are in A or they're in B, and don't count them twice. Subtract off what's in A intersect B. Okay, so this property. It's very, very simple, and it's completely trivial from the definition. What's amazing is that the definition actually defines a useful concept. But it turns out that this has a lot of the same properties as what mathematicians call measures. So for people who have studied measure theory, this is a topological analog of a measure. That will, okay, let me skip all of these, all right? Time is late. And data, let me talk about data. Okay, what is data? So they always talk about that you're supposed to connect the dots, okay, right? So data are those dots, okay? What is data? Data is really just, information of some form or other. And when we talk about data analysis, people are making an enormous deal out of data analysis. And I'm not saying not with good reason, because there are very, very good reasons to. But I want to point out, that used to just be called thinking. Okay, you get some information and you're trying to transform it and learn what that information tells you. Okay, so, there are all sorts of different methods of analysis that are suitable for different kinds of data. Okay, and you have to be very careful in what it is that you're trying to do. I like this definition of connecting the dots because it's very much, makes it sound like it's a piece of geometry, right? So when people talk about connecting the dots and discovering where bin Laden or that bin Laden is going to attack, they are having some mental picture that there are a few dots, you connect them, it draws a line, and that line will point you down to the World Trade Center or something. That was what people were talking about. And there's maybe some image like this. You could, I don't know where I stole these from. So no one sue me, please. Okay? I mean, I'm going to assume it's Wikipedia and that it was publicly allowed. So here you know, these are the dots, and we're trying to go ahead and fit them. So this is sort of what people do in machine learning or in standard statistics. In standard statistics, usually one looks at linear models of some sort, right? One will try to find a regression line, and that this one they say is just right, and that one is overfitting. So overfitting is this, when you, people do this all the time. They have a very, very crude model of something, right? And then they study it to the nth decimal place. Okay, that's one kind of overfitting. Another kind of overfitting is where you just keep adding epicycles, right? You don't want to give up your, your geocentric model of the universe, right? Despite what all the data is showing. You just add one more cycle, and then you could really get it to fit the data perfectly, okay? So those are the problems. So when we want to go ahead, the stimulus for reviewing data analysis nowadays is that there's this, so I don't think that these things are intended to replace science, in terms of discovering the deep things that govern the world. Okay, the goal is is when you have an enormous amount of data to try to organize it in some way so that you could figure out what the gist of it is. Improve on what you can do from seat of the pants. Okay, and a lot of the problem is that data is nowadays, you're measuring 50 different variables at the same time, so that puts you in a 50-dimensional space, which is very hard for people to imagine. Okay, and so you can't just eyeball it and try to get any kind of conclusions. What you really want to do is get something, and this is, so Les Valiant is a professor of computer science at Harvard, and his slogan for this game is called probably approximately correct. Okay, that's sort of the goal of machine learning. So we should catch on to it. So firstly, probably, yeah, you shouldn't expect certainty, because for one thing is you gathered the data. Forget about the fact that right? I mean, and you might have been only looking under the place where the lamp was lit. Right? I mean, it could be that there's all sorts of data elsewhere that you've just never sampled. Right? The most you could do is hope that you're probably right. Approximately correct is, again, for example, you might have noise in your data. It might be that your whole hypothesis it might be the fact that this thing is just unfathomable by the human mind, and you still want to do the best you can. Right? Right? And so, for example, if we can't predict the weather, 2 weeks hence because of various Lyapunov exponents, maybe we still could go ahead and know that it lies within a certain 10 degree centigrade range, and that might be stable for a century. That would be nice, right? So, approximately correct is somehow the best you can do. So I think that, the Rav understood some of this, and so I've redacted part of the Rav's catharsis article. And he says, science explores a world of its own making, a world of relational constructs and freely correlated conceptual series. Okay, what the scientist does is not to explain the qualitative phenomena. Okay, so the scientist is not explaining the data as it exists. What he does is he creates a model. Okay, and then, right, and that model might be wrong. Okay, it's almost certainly wrong. I mean, even to the hard-boiled person, it's wrong. That would be overfitting. If you expect to get the data, chances are you've faked your model so that it explains. If someone could explain everything, you got to be suspicious, right? It's the people who are able to say they don't know and that this is an anomaly and that you could come back to it and that, okay, there are exceptions. Ein Lameidin min haklalos. Okay, all of that is fine. He says, of course, the Rav was very impressed that we're able to create these abstract universes which you could then manipulate. So the analog would be saying, I'm only going, for what when I made fun of the statisticians and say that they like the linear models, right? I mean, there is an assumption there, and then they, of course, measure how far from a linear model it is. So now, here's how topology helps. So you imagine that you want to learn something from data, and you have two data points. One is red and one is blue. So then the dumb model would be, you just imagine that there's a straight line between them and that anything that's closer to the blue, you label blue. Anything above that, you would be labeling red. But suppose that you assembled your data and it turns out that all of the that these are the points where you labeled, but there's really a lot of other points which you haven't studied whether they're red or blue. But this is what your things look like. I think that we would all eyeball things and say that it's very likely that, why would I go ahead and say that the dividing line is this line here and that I'm going to label, say, this point as blue because it's, near that half line? I think we would more likely think that maybe it was something artificial about the way we coordinatize things, that the straight line would be the dividing line, and we would say, oh, maybe there's a circle in between here that would do this. Okay, so this is sort of how topology can help. You imagine that you have balls centered around noisy data points, and then you look for some curve that will then separate, around all of these points, and that's something that a topologist could hope to find. And then that this might be, you see, so by the way, topologists aren't the only ones who are confronted with this problem. So let me just tell you, what the old-fashioned, support vector machine people would do. They would say, oh, instead of, if you have these points and there is no one line that looks like it's really a sensible thing to do, let's look at quadratics. So what would that mean? That to each point x, y in the plane, let me consider the point in 3 space whose coordinates are x squared, xy, and y squared. So that way I will have stuck the plane in some curvilinear way in 3 space, and now what you discover is, oh, there is a hyperplane that will separate between one circle and the other. Okay? You've done it by, and then what do you have to do with this thing? But suppose that circles don't work. Oh, and I need something of degree 3, degree 4. You have to begin putting in these hypotheses. And whenever you ask the people, how do you find the kernel? They say, oh, that's proprietary, right? But that's sort of, if you like, that's supposed to be the model, so to speak. You're supposed to find the model, and then you do the best fits you can within the model. All of these kind of things, traditionally, are sort of parameterized. And the idea here is, no, you just go ahead and you form this geometric blob, and then you take your circle as being some object somewhere in the middle. That's sort of the philosophy. It's a much more topological approach. I don't tell you in advance that I'm going to be looking at curves of degree 3 or degree 9. And what would then happen is that, if I have to go ahead and specify in advance a model, or I have to find a kernel, then I'm making a certain commitment to what's the allowable form of my theories. Okay? And sometimes if you do good science, you might have some good reason to believe in a certain form, and I would not stop you from doing so. Okay? But the goal is supposed to be to somehow avoid that. Okay? So now I'm just going to give several examples where these philosophies are used in different ways in tachlis data analysis, because I thought that they were cool. But I'm not going to be able to talk about the details of anything because I'm running out of time, and I wonder if my wife is calling me now, because the talk should be over. No, my brother is. Okay, so this is a wonderful paper written by Monica Nicolau and Gunnar Carlson and Levin, I forget his first name. This was a study of women who had breast cancer, and it was some measures of gene expression and things like that. And they discovered that that all the women, they were all dots in some high dimensional space. But when they were clustered in the right way, in a clever way, using topology, they got some shape like this. And what ended up over here was this really wonderful, lucky set of women. They were unlucky because all the usual tests that doctors did at that time would make them seem completely indistinguishable from women who were having very fatal, bad forms of breast cancer. But this group here had 100% survival rate for 10 years. So that was sort of a wonderful discovery where this kind of method, the idea would be, you don't look at the data and try to chop it up according, to just look for the blob this way. You look at the data itself in the high dimensions. You try to connect points to each other. They did something more subtle. What they did was they split the data up according to level sets of a certain function. And that function was a very brilliant, I think, biological function. They were measuring, not what things looked like at the genetic level. They were looking at the expression in, how the proteins were actually expressed and measured in the bloodstream. So therefore what happened is that women who were succeeding in unexpected ways became visible. So it was that even though, so the point is, so that if you look at them through the normal lens, they just said, oh, these women are abnormal, so things are going wrong, and you therefore think that they're going to die. But happily, it turned out that there was a set of women who were doing things in a completely non-standard way, and that was detected this way. So this is a paper that appeared in 2011. My point of view on all of these results is that this is not mathematics. Okay, there are no theorems here, there are no hypotheses to verify, and it's not like statistics where you could say, oh, maybe it's not a Gaussian, but it's close enough so that I could try to apply a central limit theorem or something. This isn't that. Okay, this is some kind of methodology that's suggested by geometric insights, and and then when you apply it, you don't get a result, you come to a conclusion, and you hope that you're probably approximately correct. Okay, that maybe the geometric figure is a bit off, but it has, sort of the right overall shape for doing things. So it then should be a hypothesis for further study. So for example, finding genetic markers for this kind of thing, doing tests with larger cohorts of women. Right? There's always a problem about false discovery when you do such studies. This is much earlier. This is before the words topological data analysis came into the popular lexicon, to the extent that it has. This was a study done also at Stanford, and this was a projection into three-dimensional space of a set of people at a hospital, some of whom had diabetes, and it turns out that when viewed the projection into three directions, which are labeled here and I'm not going to explain, these turn out to be the normal people. So the whole thing looks like a blob. To a topologist, we would say it's connected, right? Naively, you would say, oh, this means that there's one cluster. But then you begin looking at the labeling, and it turns out these people have diabetes and those people have diabetes, and these people are normal. So that suggests that the thing that we call diabetes is really two diseases. Well, and we know that that's true, that type 1 and type 2, and that they have different genetic markers. They both have something to do with insulin. But this was sort of a geometric expression of that fact that was done in 1985. This is another very lovely, interesting problem that I think led to. So again, the idea is going to be, instead of just connecting the dots to draw lines, we want to put things together and imagine that they're coming from some higher dimensional object. Okay? What can that object look like? What could organize our thinking about the problem that we're dealing with? So Mumford, who was a Fields Medal winning mathematician, then moved into computer vision, was very interested in the following question. He said, you look at this, there's a data set full of natural scenes from around the world. These were just black and white photographs of things that you might see if you were a being living in the universe, living on Earth. Okay? And your vision system has to deal with these. And we know that the vision system doesn't deal with the whole object at once. It breaks it up into little parts, and that small pieces are dealt with by different neurons and so on. So you want to know, what's the job that the neurons have to do? How hard is it? Is there anything special about the images that we see when we see images? And so he broke everything up into 3x3 little pixels. So these are huge, right? So each picture like this is an enormous number of these little patches. Now a patch that's 3x3 pixels, each of them has an intensity, so it's a real number. So you have 9 real numbers so each of these things is a point in 9-dimensional space, and you have thousands of points per picture, right? So you have this huge data set living in 9-dimensional space. Okay, then you say, well, the light intensity is ridiculous, that's an irrelevancy, I mean, sometimes you look at sometimes it's dark outside when you look at the trees, and sometimes it's light, so you rescale, so it's really living on an 8-dimensional sphere. And the question is, what does this data look like? Is there anything special about the things that the eye has to solve when dealing with the pictures that it's confronted? Just the black and white pictures. Okay, so they compute a persistent homology, but I didn't talk about homology, so I can't tell you. But they came up with, ultimately, a model, and I didn't write down it turns out that most of these little 3x3 patches live not far from a Klein bottle living in that 8-dimensional sphere. Okay, and this is a picture of that Klein bottle. Okay, so you imagine just like the square, but now you identify this one going up with that one going down. And when you do that, this blue circle becomes identified with that one. And, whoops. And this is what they call the three-circle model, which is, that part of the data, when looked at one scale, looked like it had 5 holes in it, rather than a Klein model, which has, like 1.5 holes or something. Anyway, so the question was, how in the world would you be seeing, something that looked like it had 5 holes? Well, if you count this has, okay, remember these circles don't really go through each other. If you count things exactly right, you would see 5 holes. But, and this is part of the Klein model. It's part of this Klein model with the colors all put together. Anyway, so that was sort of an interesting thing. And again, it suggested various things, like, for example, checking whether the neurons deal differently with, when the retina gets an image that's near the Klein model, does it deal with it differently than for 3x3 clusters that don't, that are further away, right? It's a question, does the brain actually use this method anyway, right? I mean, that was what Mumford was interested in. He was interested in, say, compression, right? So we do know that now natural images seem empirically to be rather special. Even though we thought that they a priori could be living in an 8-dimensional space, the way we parameterize them, they're really fitting into something much sparser than that, a two-dimensional object. And the two-dimensional object, by the way, was that really cool Klein model that doesn't fit in 3-dimensional space, right? You thought it was a mathematical curiosity. Well, it could be that that was what you needed to understand in order to develop vision. This is another cool application of topology. The main author is missing from here. It's Vanessa Robbins. I don't know how she got cut off. She was one of the earlier people to define persistent homology. This application, by the way, is not to data analysis per se, but it's really wonderful. They were interested in mapping Alaskan snowfields. And you know what Alaskan snowfields look like? They look like snow. Okay, lots and lots of snow. But you need to map them because if you're going to, fly from one place to another, as you're very likely to, you want to land on a place where the snow is solid, not on something where it's essentially melted and it's just a thin veneer over a big puddle, because when your plane gets in the water, it's bad. Okay, right? So there are all sorts of reasons. People find this extremely boring. They're able to do it. They could look at something like this and figure out what it's supposed to be. You'd like to really mechanize it. So topology provides such methods. You go ahead and you look at an object and then you imagine increasing, just formally saying, I'm going to increase the size of it by, half an inch or something, and just see when various things close up. And it defines purely mechanically invariants that could be computed by, computers, assigned to places, and develop heuristics and provide maps. And I believe that was what Vanessa did right after her thesis. This was cool. I saw a DARPA presentation of this where someone was walking around and his chest was being outlined by mechanically. The trouble is that when I move around and walk, right, I in detail change as a point set, right? But as an abstract object, I'm staying the same. So for example, the guy obviously was intending, to follow. There was a red dot on my heart, in the DARPA presentation. It really was cool, but ridiculous. But it was, again, some method of following around the points. I think that I'm going to, this is really this is beautiful, and this goes back to the original Euler characteristic stuff. I think that this might be close to the last application. So this is work that was done by Robert Adler at the Technion and Jonathan Taylor at Stanford, and Keith Worsley, who was at the time at McGill but moved to Chicago. And here the idea was, and this is a matter of trying to understand the statistics of MRIs, or also there are lots of things there are lots of important things that are two spheres. Okay, like your brain is a two-sphere if you're a really bad modeler. Okay, right? You ignore all the folds and everything else, and then you say, oh, to a topologist, that's a two-sphere. Okay, or there's the universe. The universe isn't a two-sphere, but if you look out, to the edge of the universe, right? There's the celestial sphere, so to speak. Okay, which is where the cosmic background radiation lives. Okay, and that's also a two-sphere. So now you have all these very, very carefully measured functions, right? Like MRIs are one kind of measured functions. Well, they're actually quite noisy. And, but on the other hand, cosmic background radiation, we spend billions and billions of dollars and create all sorts of satellites to measure and so on. And the question is, you see all of these kind of complicated things, and the question is, maybe what you're seeing, how do you tell what's data and what's noise when you see pictures like this? And the basic method turns out that standard statistics doesn't sort of enable you to model the extrema very well, but there are formulas for getting expected Euler characteristics. You see, somehow, getting a probability is really hard, but computing a volume, that's calculus, and then Euler characteristics, as I told you, behave a lot like volume. So there's a formula called the Gaussian kinematic formula that's in a book by Adler and Taylor, and that stuff is routinely used in MRI data analysis. Basically to see that you go ahead and you see something and you want to say it's an activation. Well, maybe that's just a random fluctuation. How do you go ahead and decide that? How do you compare two different, right? You're trying to compare two different pictures, both of which are insanely complicated to the human eye, and you're not trying to even compare them to each other. And registration problems if you're trying to compare different brains, right? You also want to deal with the fact that they're both noisy, right? And you don't know what else is going on, right? You say you're doing an experiment about looking at donuts, but maybe besides looking at donuts, in one case there was noise going on in the outside and the other one there wasn't, and you want to be able to, that's a funny, I didn't mean noise in that sense, but anyway. Okay. This is work of my student, but I don't remember when I started, so I therefore don't know absolutely when I'm done. Again, here's a matter of trying to measure the difference between various kinds of bones. And again, there are topological methods that come out, that wouldn't be so hard for me to describe, but here the key point is that they're mechanical. They don't involve having graduate students labeling points on each bones and trying to align them. They're completely mechanical kinds of things, and they work pretty well for clustering. So now you could see we got to the point where I ran out of things to steal. So I had to write out. So there are so all of these kind of problems. There's of course the scientific problems. I gave you various scientific examples that I think are exemplars of where these ideas, have done things that are interesting. I haven't said that they've done things that are correct. Okay, because I don't know. I think in all of these cases, their value is in suggesting hypotheses that you then have to verify. You have to find other experiments to test them. You have to make predictions. You have to use them. The proof of the pudding is in the eating. Okay, Latke Tash debate line. Okay, it suggests mathematical questions like when and how can reconstruction be achieved? You imagine, right here we were imagining that we're trying to achieve this Platonic goal. You're given the points and then you want to connect the dots to find an underlying geometrical object. When in the world could that be done? How many points do you need for such reconstructions? All of these are mathematical problems which have produced a large literature in recent years. But that's the problem of forgetting about the fact that the data that you have is noisy. That would be, suppose that you just wanted to do reconstruction. But what is the role of noise? Very, very large. There's a growing literature. I would say that it's really in poor shape. There's the question, how do these tools mix with classical statistics? What do we mean by random topology? Okay. The last one is the one that I'm personally most interested in these days, is that there are unfortunately theorems that say that all of these problems are hard. If you'd want, say you want to go ahead and, so there are theorems, you're going ahead and you're trying to find a structure to enable you to do something else. But suppose that finding that structure was as hard as answering your original question. Well, that would be bad. Okay, so what we've discovered is that finding topological structures, it depends a lot on the nature of the structure. 0-dimensional, 1-dimensional structures, 2-dimensional structures are fairly computable. By the time you get to dimensions, there's a phase transition. So 3-dimensional structure or 2-dimensional structure with singularities are both, there's sort of a phase transition in computational complexity and description complexity. I mean, it's just, there's a big gap there. And the question is, are there things that are less than discovering the whole geometry that can be useful to us? Like an Euler characteristic. That's a quick summary. Vertices minus edges plus faces. You can compute it pretty quickly. How useful are such things, right? Can we find more invariants that are less than everything, right? Because everything is too hard in this data-rich world, okay? Or too expensive if the data, if it sort of requires, more satellites in order to generate more data and so on, right? So the question is, what can be done in terms of what can be computed? I just want to end with a little caution. So I've already cautioned that there aren't really enough theorems to support the practice, and that the practice, in all cases, I don't feel leads to truth. It only leads to hypotheses. But there's this interesting book by Kathy O'Neill from a couple of years ago called Weapons of Math Destruction, that's a general warning about the overuse of machine learning. And machine learning is used nowadays in many settings, and one example that I think is particularly heinous is that in many places, in order to avoid judges and parole boards from being prejudiced, is they say, okay, we want to do things objectively, and the judge won't have any, will be given, either they'll demand that he actually use a machine learning model, or that he will be given an advisory report about how likely is it that this person will reoffend, or things like that in terms of deciding, say parole issues, or what the length of a sentence would be. And if you think about what's involved with that, for one thing is, we don't really understand these machine models, right? You go ahead and you put in the thing, you say, I'm going to use fourth degree equations. The analog of using fourth degree equations is, I'm going to go ahead and look at the people in his neighborhood and see whether or not they're going to commit crimes or not, right? I mean, the question about which kinds of functions you use, right? If you like, the characteristic functions of which sets are allowed into your support vector machine is a matter of you deciding which things are going to be relevant. And and certainly for issues of, we as a society have sometimes thought that the question about what your punishment is not based on the things that you're going to do, but the things that you have done. And certainly it shouldn't be based on the people who are similar to you by some set of easily checked characteristics, right? Like whether your father lives at home or not, or whether he was in jail. I mean, there are all sorts of things that get into these kind of reports. And they could be just very sophisticated ways of, not explicitly, but implicitly putting in your own biases in that. So that's a problem. I think that the Rav said it very well in Catharsis. So first, as we already pointed out, we could attain knowledge and understanding cosmos only when it's translated into quantitative abstract construct. We have to understand that we'll never understand the link between the mathematical idea and the event. Okay, this is the business that our models could be wrong and we're necessarily going to have errors based on the model. I mean, the Rav said it much more poetically, but that's fine. Okay, the next point he made, though, is I think the point that we really have to think about, which is the moral law can never be legislated in ultimate terms by the human mind. I mean, we have to think about when we want to apply these things in any kind of ethical situation. This shouldn't, it shouldn't be the rule that you go ahead and you take some machine learning model, go ahead and say that it gives you some number that you don't understand, and that's the reason why the person should be let out into society or should be kept in jail for 5 more years. Okay, that's it, and then there are a bunch of references which I don't know if there's any use in me showing you, but okay, that's it. Okay, thank you. Yeah. Oh, you can get the references from Professor Diamond.
Want to take questions? Or?
Yeah. I could talk forever. Yeah.
How would your feelings about these machine learning models change if there were studies done that showed they were very often correct? Let's say they had 90% accuracy or some other...
I don't have to answer that with an answer. I'll answer it with a question. Okay? How would you feel if there was an oracle that you could go to that would predict absolutely accurately? It says this person will commit a crime in 3 years and 2 days if you let him out, and he won't if you leave him in jail. And then every single time that you let a person out, he committed the crime on exactly the day that was predicted. How would you feel about using that?
I agree. It's the same question.
Okay, so I think that's the question that's that needs to be discussed. Okay, but it's not a scientific question, right? I mean, yeah. Yeah.
Could you give me an example
example of you asked what is noise. You also did the overfitting, which was the overfitting
Right.
versus regular fitting. Could you go back to the quadratic and give me an example of something you would say, this is a legitimate quadratic, and these points the points around it are noise? I mean, just an example here, so you have an idea of what might be noise.
Well, that example wasn't built to be noisy, right? I mean, this was an example just, you know.
Further on, when you were fitting a point.
Oh, over here.
No, further beyond that. And when you said you had
points in the
underfitting.
Further back.
Overfitting.
Yeah,
That's a statistic, that's it, yes.
right. Right?
So I mean, what's a good example for you in terms of just right here? That's an example, because then if you know what just right is, then you can know what noise is.
Right. So the point of view that I would have about the topological things is this, that it is a different solution to the question of overfitting than the one that the machine learning people do. The machine learning people their solution is, we don't want to look at a function space that's this complicated, because even with this one we have errors and that it isn't completely fit. We just say it's overfit, and the point is that we put in too much complication for the purposes of explaining this data. Okay, right? But if you go ahead this looks like it's only a slightly more complicated function space than this one, and for that little complication you have so much of a reduction of error. So, right, I mean, this is still art, right? I mean, exactly these trade-offs, you know, there isn't a very well-defined way of doing it. The topological solution, so to speak, is this. It's saying, when I view the answer that this data is topologically a Klein model, I'm viewing that as a complete, you know, as a non-overfit solution, right? Because I found a simple geometric object that explains a lot of the data by definition, you know. Okay, then you run it then creates a second problem, by the way, which is you now have, say that your data is a Klein model, suppose that you're trying to do a predictive process, then you go ahead and you now have to go ahead and do function theory on a Klein model rather than function theory on R8, on the 8 sphere. And the point is that hopefully that will be easier, okay? You know, but
I mean, you don't have a specific example for your quadratic there, which, you know,
no. Yeah, I don't. I think that, you know, this looks to me likely that it is a quadratic fit.
I agree with you.
But, you know, I was just trying to convey a philosophical point rather than.
No specific thing.
I don't have a specific thing in mind, although I don't think that I'm, you know, just BSing. I mean, I think that, you know, but I don't have a specific thing that I could point to right this second. It's not on any of the slides. Yeah. You know. But maybe I am. Okay.
Any other questions?
That paper you put at the end about something Chazal and something else.
Oh, Chazal is not Chazal. It's a Frenchman named Frédéric Chazal. Okay. Very, I mean, he's a very good geometer. He works at outside of Paris at a place called INRIA.
Okay, so that's less exciting.
I'm sorry, yeah, no. But yeah, so he's written a very, very lovely book with Boissonade and Udo, Computational Geometry and Topology for Data Analysis. It's coming out this coming year in Cambridge University Press, you know, I mean, it's sort of very good. I mean, it really mixes geometry and topology and analysis and computer programming and stuff like that, and some statistical ideas in a very nice way. I mean, it's, you know, it's sort of state of the art without a lot of, but it isn't like a how-to book that has, you know, lots of actual applications in it. For those, I think that still one has to look in the literature and then use taste to find the ones that you like and throw away the ones that you think are bogus. So I just sort of gave you an opinionated list of papers that I think, you know, did cool things using these ideas. Yeah.
Although you don't have any theorems on this, why do you say this is not mathematics? It looks like it's mathematics to me.
Okay. I mean, firstly, you know, It certainly uses mathematical ideas, right? I mean, and the things that are, and one computes things and one computes homology groups and so on. But there's no theorem out there that I cited that says that if you actually compute this homology group, it tells you something. It doesn't even say that if you do this calculation twice, you're going to get the same answer. Okay, right? So I mean, so it doesn't. There are some theorems that actually have that form, that you go ahead and you take something and you sample it, and that if you sample it twice under suitable hypotheses, you will get the same answer with high probability. Okay, there are theorems like that, but since I didn't actually express any of those theorems, it wasn't quite mathematics yet. Okay, right? But yeah, so that was all that I meant. I mean, yeah, there was another question that I didn't.
I don't see how you really answered the previous question about noise, because all you said is, here's an easy case. We have a very simple shape that expresses the data very well.
Yes.
So obviously, in this case, we're going to say we'll go with a simple shape. We have, again, a simple shape that expresses data well.
Mm-hmm.
But how is this any different than the normal trying to fit lines and other shapes to data? All you're saying is now we'll do more than just fit lines, we'll fit more complex shapes to our data.
Mm-hmm.
And it's still the same question.
Yeah.
How do we fit
Okay.
how complex a shape is appropriate?
That's a great question. And there's sort of another, and it's and it's even deeper than it sounds at first glance, actually, because for people who know linear algebra, okay, you might study a vector space, and then you study the dual vector space, and the dual vector space is the linear functions on the vector space. Okay, so firstly, so you sit, and then you build a space out of the dual space, right? The dual space is a space, and you could study either of those geometrically, or you could study them as function spaces. And there's some kind of function space duality that goes on. Okay, so if you look in the subject of topology, I mean, how is it that topologists prove their deepest theorems? I mean, there are some very deep theorems that were proved already starting in the 20th century. And a typical maneuver that topologists do is they start off with a geometric situation, they associate a function to it, and then they study and then they study properties of that function. Like, in algebraic topology, you have homotopy groups that are built out of maps from spheres into your space, and so on. So, the idea that something is geometric on one side and versus, function theoretic on the other side, it's both true and and not. I mean, it's not right. I mean, Hilbert space is a infinite dimensional space, and it's built out of functions. Of course, if I'm going to think about a function like sine x and say it's merely a point in a Hilbert space, I've thrown away all the information about sine x, and I'm only maintaining its relationship with other functions. Okay, so but anyway, so I think that one could make too much of the distinction between functions and spaces. But there really are different attitudes that come up from looking at things from either geometrically as opposed to analytically. Okay, and part of the goal is that to try to find useful methods, and so that's also why I don't really believe that there's this general subject that you go ahead and you armchair and you sit and think about, oh, what is a good method of data analysis? This is something I'm going to always apply it. For example, with support vector machines, I mean, I made fun of them, but they really are right when they say finding the kernel. Oh, well, that's proprietary. That involves some subject knowledge or something like that. Yeah, you shouldn't expect that there's going to be an off-the-shelf thing that's going to solve all your problems without feeding in some hard-earned theoretical knowledge in advance. So the question is, some things are simpler to view geometrically to human beings or for the purpose of computing homology. You could associate a persistent homology group to a function if you were so wished. How would you do it? Well, you'd be thinking about geometric objects associated to the functions like level sets and sublevel sets and things like that. It's a different method of processing. So there are some things that, that seem geometric, but I mean, a lot of it, I could think of a space as being the same thing as the characteristic function of the space, and now have embedded all of geometry within problems of analysis of some function space. But that wouldn't be useful, because all that it did was it made an artificial translation into a world where that thing doesn't matter. So the point is that I think very convincing it was Raven Miller diabetes case where, you know, the object was in some space of various metabolic functions. It was a high dimensional space. They used standard statistical PCA methods to find a three-dimensional projection. When they found the three-dimensional projection and looked at it, and, you know, it had this weird shape, but then when they began labeling the points, they said, oh, these are normal people and these are two others. And then, you know, and I think that you would say they didn't know the shape in advance, you know, but the belief that there existed a shape guided their analysis. So I think that that's sort of the point in topology. It's not going to always be suitable, you know, and sometimes you're going to do a lot better, you know, like, a lot, you know, I wouldn't go ahead and, you know, begin telling engineers when you see a signal coming in, you know, stop using Fourier series and begin eyeballing it and computing homology groups. No, I mean, I'm not that ideological, right? I mean, you don't have to throw away the successes of other methods. But I think that the point is that you should also look for the geometric thing and then combining the two. Basically, you know, one way to say it is this: that if you're looking at functions on S8, you know, that has some kind of entropy that grows exponentially with respect to, say, the Lipschitz constant to the 8th power. If you go ahead and say that it's really living near a Klein bottle, you lower that L to the 8th to an L squared. So so that geometric analysis could be a step towards, you know, then doing vision processing in a better way. You know, but yeah, it does. I don't think that this is supposed to be stuff that does things all on their own.